Okay, so we're doing recitation number 2, problem number 3. And so this actually has to do with the angle of incidence, light reflecting off a mirror. And a couple of key ideas before I actually do the problem and explain the idea. So when light hits some kind of a mirror, let's imagine light has a mirror, okay? So this is our mirror. Light basically comes in at an angle and then bounces off. And again, let's put the normal surface, right? And ask ourselves, okay, what's going to happen in the reflection? So here is the incident ray. Here's the reflected ray. Okay, so it's a light ray coming in, bouncing off. Now, the main thing is that the mirror, what it's doing, right, is the main concept in a mirror, right, is that everything in space over here is being reflected onto the upper surface. So it is a reflection. So what we're actually seeing is that if we could actually imagine that this light ray was going through the mirror land, right, it would be a straight line. It would be a straight line in the mirror land, the reflected material. So it's going straight through. Light always travels in a straight line, but it's being reflected right across the mirror. So this thing is being bounced back, reflected. So there's a reflection plane right here. The mirror acts like a reflection plane. Basically that reflects this light ray that would have gone in the mirror world and being reflected back on itself. So if we know this, right, we know that this angle, right, theta, right, over here, this incident angle from here to here, this angle, must be the same as this angle. Theta, let's call it 2. Should look over the notes. But if it's reflected onto this side, right, then it must be this angle also. So what you're saying, right, is that this angle must be a reflection across this line. So whatever this angle is here must be the same as this angle because they're reflected. And so this angle must be the same as this angle. And so most people just memorize this and say that the angle of incident is equal to the angle of final. So this is the main concept you want to get across when looking at angle of incidence equals angle of reflection. And I have no idea why I keep putting F. I think it's a habit. I always put final F. Incident and final. Anyway, so here's our angle theta. So that's the main thing we have to learn. In your recitation problem, right, we're asked, right, that you have some kind of a mirror, 2 mirrors actually. So here's our first mirror. And we're told, right, that there is a light ray coming in. And we're given the incident angle, and I'll make up some numbers. So let's say it's 30 degrees. I like nice easy numbers, 30 degrees. And so this is going to get reflected. And the question is, we're also told, right, the distance from here to here. So let's make up some numbers. Let's say the distance from here to here in the first mirror plane, right, happens to be, don't want to use the same numbers. So let's say it's 2.5 meters from there. Okay, so we have a light ray coming in. So using our ideas of mirrors, right, we know that the angle of incidence must be equal to the angle of reflection. So or after. So here is theta F. So that's 30 degrees. So from here to here must be 30 degrees. So this light ray comes in and it's going to hit this second mirror. And one of the first problems we're asked, right, is first, what is the distance from here to here? And this is actually so we have to remember sines and cosines. And so here is so if this is the distance 2.5 meters, and this 30 degrees, the reflection here, 30 degrees is here, then the distance from here to here, which is 2.5. This is 2.5 meters also. But I know that the ratio of the opposite leg of this triangle, it's a right-handed triangle, to this length L, right, which is what I'm looking for. So find the distance the light travels from here to here. So let's call this L. So all I know is that the ratio of 2.5 to L is the sine of 30 degrees. And sine of 30 degrees, I chose 30 because it was kind of easy. I don't have to bring out a calculator, right? So that's actually equal to 1/2. And so if I solve for L, that would be, so multiply by 2 on this side and multiply by L on this side. So move the L to the opposite side, inverse transformation. 2 is being divided, so you multiply on this side. So L is equal to 2.5 times 2, which in this case is 5.0 meters. So we're expecting L to be 5.0 meters. So again, the ratio of this length to the length L, right, is defined as the sine and cosine. I would highly recommend that you always memorize these rules. I know there's a couple of mnemonics to help you remind sine and cosine, but you should just memorize it as much as possible. Just to remind you, if you're given a right-handed triangle, so let's call this y, x, and this is r, and this is theta. So remember, you have to memorize these things. So the ratio of y to r is sine of theta, and the ratio of x to r is cosine of theta. And of course, the ratio of y to x is tangent of theta. So these are things you should memorize so that you become familiar with these equations, but they should become natural, especially if you're doing science. You tend to do a lot of these problems. I know majority of you guys might be in biology, but that's okay. So you should memorize these rules because you never know. You probably will be doing these calculations somewhere in your career. Okay. Anyway, so the second problem, right, was that we'd have to calculate the angle. How's the reflection, right, of this light ray? So let's imagine, here's your 30 degrees, so let's call it theta. So this is theta is 30 degrees, this is theta also, but we know that this angle plus 90 degrees is 180 degrees. So if you think about it, this angle, right, must be 90 minus theta. So this is 90 minus theta plus 90 is 180 degrees. We know that the sum of all interior angles in a triangle is 180 degrees. So this is 90 minus theta. And you might say, well, I don't fully understand what does this have to do with things, but think about the complement. So this is 90 minus theta, but then the complement here must be theta. So what you're saying is that the light ray, this acts like a normal. Look at this normal here and this normal, right? So this angle here is theta degrees. So the light ray coming in has an instant angle of 30 degrees, and the light ray leaving is 30 degrees relative to this angle. This normal. This is parallel to the mirror. So what you're saying is that these two light rays, they're parallel to each other. I haven't drawn them properly. It's a terrible drawing of everything because these two light rays are parallel to each other. So the exiting light rays are actually parallel to each other. So one light ray comes in, it bounces, and comes back parallel. They should be parallel, but my diagram is horrible, and I'm not a great artist.